Thank you very much for the introduction and for the invitation to speak here. It's very exciting to be here. And it's a pleasure for me to follow the wonderful talk by Professor Porter. I'm going to be talking today about AI and robotics, and start by presenting a goal of AI and robotics, which is actually perfectly set up by Professor Porter's remarks, in the sense that it's exactly the goal of not being narrow. This isn't everybody's goal, but of all roboticists in AI. But my goal, and people like me have been striving for years to try to create robust, fully autonomous agents in the real world. And to be able to be fully autonomous and to be robust, it exactly requires not being narrow. You can't just be capable at one single task. The real world throws lots of unexpected things at you. So a question is, how should we go about doing this? And again, to follow on the historical perspective of AI, at the beginning of the field, 60, 65 years ago or so, there was really no choice. If we wanted to try to build complete agents, we'd have to break down the task and into various subcomponents. Computer vision, some people would work on, natural language understanding, others would work on, planning, manipulation. All of these things became sort of sub-areas of artificial intelligence, each worked on by individual separate communities. And when you're starting from nowhere, you have to start from the bottom up in that way. But over the past few decades, myself and some of my colleagues have been able to take the opposite approach, standing on the shoulders of the people who started from the bottom up in this way, which is to take a more top-down approach, to create complete agents to perform increasingly complex tasks. And so this is, and when I say complete agents, I mean agents that can sense their environment, decide what actions to take, and actually execute them in the environment. So for instance, the chess-playing program Deep Blue did one of these three things. It did the decision-making, but it didn't have to sense where the chess pieces were. It didn't have to move them itself. That was done by people. And the idea of trying to build these complete autonomous agents is that it will, this integration approach will drive new research on components, algorithms, and theory in sort of a top-down pull kind of way instead of a bottom-up push kind of way. So in this talk, I'm going to emphasize two aspects of complete agents that I think are very important. One, again, foreshadowed by Professor Porter, is machine learning. An autonomous agent that makes the same mistakes over and over again and doesn't learn from its experience is not going to be considered intelligent for very long. And so that's the sub-area of machine learning focuses on this. The other core component that I think is very important for robust autonomous agents is interaction. A lot of the intelligence that we exhibit as people is the ability to interact with one another, to understand each other's goals, to be able to interact in a social world. And so the area of multi-agent systems focuses on that. So in my lab at UT Austin, I do many different things. I actually do some of the bottom-up style research, as I talked about, working on sort of fundamental new algorithms and theoretical approaches to AI. But a big part of my work also starts from the top down. And if I'm going to give one slide introduction to all of the things we do in my lab, it's going to be the applications and the motivating applications that I can emphasize most clearly. And so that's what I'm going to do here. But first, the question that sort of ties all the things we do, and it's motivated by that previous slide, is to what degree can autonomous intelligent agents learn in the presence of teammates and/or adversaries in real-time dynamic domains? And this is a sort of a complementary form of not being narrow. It's the trying to figure out how to act, and the theory of actions and the effects of actions. I think that's one important part of robustness, and then being able to leverage language and reading is a separate part that need to be put together. I'm going to focus on the first here. First, the research areas within artificial intelligence that this question leads me to are the ones you see here, and especially machine learning, and a particular type of machine learning that I'm going to emphasize and give an introduction to, known as reinforcement learning. But just before I do that, I said I'd give you some ideas of some of the application domains. John, in the introduction, mentioned that I do use robot soccer as one of the application domains. And so here's a video from about 10 years ago, some of our robots acting fully autonomously. There's nobody with a remote control. There's one of our robots scoring a goal. These were the Sony Aibo robots that were actually discontinued around that time, and Sony has excitingly announced that they're coming back later this year. But to be able to do that, to show it again, there's lots of different capabilities. The robot has to be able to see the vision aspect. It has to be able to localize itself, figure out where it is. It has to coordinate with its teammates. And when Sony did stop making those robots, we moved to a different robot platform, but still within the standard platform league of RoboCup. I'm going to talk more about RoboCup later. But these are our robots from the ones with the hands behind their back here are the ones from our team. This was the finals of the 2012 competition in the Standard Platform League. We were playing against a team from the University of Bremen. And again, no remote control. The robots are having to do this all by themselves. Here's our robot going in on a breakaway. You'll see that it's, again, it has to see where the ball is, figure out where itself where it is. And here you'll see it approach the goalie and calmly bank the ball off of the goalpost and in. So that was the first of our 4 goals on the way to a 4-2 victory. And when we came back this was in Mexico, when we came back to Austin, they lit the tower orange for us, which they usually only do for the football team, so we were very proud of that. So this is, this is an example of sort of a grand challenge domain that I'll talk about later that sort of integrates many aspects of artificial intelligence and itself pushes forwards research. Another application domain that's very in line with the language focus of the previous talk is the following. We're working on a platform of robots that we call the Building-Wide Intelligence Project. If you come to my lab down the street, the 3rd floor of the computer science building, you'll often see robots like this just wandering through the hallways. You don't need to ask us for a demo. They're just around there. This particular video is the robot's moving 4 times the speed. It doesn't move quite that fast if you're in the hallways. But this particular video was part of a collaboration with my colleague, Ray Mooney, on grounded language learning. And very much in the spirit of Professor Porter's remarks, this robot we deployed for a whole week with a very limited language model at first. It knew, for instance, one way to say, lead me to Peter's office, or lead me to office 3.508. It knew one way to say that. It knew what the office number was. It also could deliver things like coffee. But it didn't know the rich, sort of varied ways in which people will communicate these things. And it learned during the course of the week through dialogue to improve its understanding of language. So for instance, a person might have said, I want to follow you to Peter's office. The robot says, the robot might say, what is it you want me to do? The person will rephrase, please lead me to Peter's office. The robot then might say, oh, you want me to lead me somewhere. Where is it that you want to lead me? The person then says, office 3.508. At the end, the robot understands what the person wanted. It's sort of through a dialogue, but it can use all of the previous ways that the person uttered that sentence as training examples to improve a grounded language model so that in the end, in the future, when somebody asks, to lead me to Peter's office, or I'd like to follow you, it knows now where my office is, what the different ways people can say these words are. And by the end of this week, we were able to find that people could, with shorter dialogues, get their commands fulfilled. They were less frustrated. We didn't type in the meaning of the language. The robot was learning in a grounded way what the meaning of this language was through experience. That's just one example of the types of research we do in this Building-Wide Intelligence project. We have multiple robots. They do activity recognition. They're trying to become part of the social fabric of the building and learn how best to interact with people. So that's another example of sort of an integration challenge that requires the vision, the language, the planning, the multi-agent reasoning all together. Another that I've been involved in is I did have a car back in the DARPA Urban Challenge. So this car back here in 2007 is one that we took here from UT Austin. The cars on the inside loop are all driven by human drivers with helmets on, looking sort of scared, but our car did not run into them, so it turned left here. It then had to find another gap in traffic, and it made 8 loops in about 20 minutes. This was back in 2007. Now, of course, as you know, all the car companies really are investing big dollars in creating autonomous cars. So we've retired our prototype research vehicle, but we're still thinking into the future of what the world will look like when all the cars on the road are autonomous. Will we need traffic signals and stop signs? Or will intersections look more like this? This is what I think we'll be able to do with autonomous cars, taking a multi-agent systems perspective. What's going on here is instead of a traffic signal, there's a program at the intersection that's managing a reservation table, and the cars are calling ahead for exactly when they want to go through the intersection. And the ones that are white already have a reservation. The ones that are yellow don't, so they have to stop. But once they turn white, they have a guaranteed path through the intersection that won't collide with any of the other cars. Now, we showed this back in 2003. We've been doing sort of more than a decade of research on now how can we integrate this with human drivers? How can we scale this to a larger city? The first time I showed this, I was at a conference in India, and everyone said, wait, that's what all the intersections look like. But the difference is that here we can guarantee that if the cars follow the protocol, there won't be any accidents. In the same way that if no human drivers drive through a red light, there won't be any accidents. So these are the kinds of application domains that motivate me in my research, trying to integrate the aspects of artificial intelligence that are being developed independently and trying to figure out how to create robust, fully autonomous agents capable of learning and multi-agent interaction. So the thing I wanted to emphasize, I'm going to dive down now into sort of a technical perspective here a little bit, to give you what I think is one of the most important aspects technologically of artificial intelligence moving forwards. Again, in a way that, for the reason that we want to try not to be brittle, not to be, and to be, not to be narrow, to be as broad as possible, and to learn, and to have agents understand knowledge at a root, a very basic level. So, as Professor Porter also said, machine learning is a very exciting capability, but it has limitations in its sort of business as usual type uses. And the distinction I'm going to make is between sort of two different types of machine learning. Almost everybody who's using machine learning these days in industry is using what we call supervised learning. Supervised learning is the type of learning that is just given a set of data and learns correlations. So, for example, if you're given a bunch of handwritten digits and their labels, you could get hundreds or millions of these. It includes 4s, 3s, 1s, and of course 8s as well. And then you have to learn a function that says, okay, what is this? Okay, and you can do this. You can do supervised learning of this type without really understanding the algorithms behind it. There's general purpose, very highly capable tools out there, such as TensorFlow, that's just one. There's MXNet, and there's Torch, and Theano, and Weka from a while back, that will allow you to do supervised learning if you can just present your data in a format of a batch of data with labels on it. The type of machine learning, however, that's much more appropriate for building robust autonomous agents, and which I've been involved in my research for the past 2.5 decades or so, is known instead as reinforcement learning. And this was a small niche area of machine learning until recently. It's now gotten into the public vernacular a little bit for a variety of reasons, which I'll highlight shortly. But the difference of reinforcement learning between reinforcement learning and supervised learning is that it's learning about the effects of actions, okay, through experimentation. And again, this allows for the grounded learning of knowledge, not by somebody typing it in, but by the agent getting experience. And so the paradigm for reinforcement learning is that an agent, rather than learning a function that it has to generalize, it's an agent that's learning a policy, a mapping from states to actions. So you can think of that as, if on a chessboard, it would be from the positions of all the pieces to what action would you take. Or if you're driving from home to work, given the intersection that you're at and the traffic report, whether should you turn right, turn left, or go straight. And the idea is that you take that action, execute it in the environment, you end up in a new state, and maybe you get some reward, but nobody tells you whether it was the right action or not. The algorithm itself is responsible for, at the end of the sequence of actions, figuring out what were the good and bad decisions. Right? If you lose the chess game, it's not the last move that was the culprit. you have to go back and figure out what were the good decisions and the bad decisions in your sequence of actions. And same thing, when you drive to work, if it took you twice as long as usual, it wasn't your decision at the last intersection that was the culprit. So reinforcement learning algorithms have to do what's known as the temporal credit assignment problem. They have to solve that. They have to assign credit and blame to the history of actions over time. The other big difference from supervised learning is that they're not given a batch of data. They're responsible for generating their own data, for experimenting. If you play the same opening in chess every single time, you'll never learn what would have happened had you taken a different move. Same thing, if you drive the same route to work every single day, you'll never learn what would have happened if you'd taken something else. So the reinforcement learning algorithms have to balance between exploration and exploitation in this way. One of the ways of formalizing a reinforcement learning problem is what's known as a Markov decision problem. Due to time, I'm not going to go into some of the details here. But there was some very exciting theoretical results in the early 1990s, late 1980s actually, that you can, using a particularly straightforward algorithm under a set of sort of clean assumptions, find the globally optimal policy in a reinforcement learning problem, not get stuck in local minima. The problem is that the assumptions were very, very narrow, and to try to get reinforcement learning to scale up to big applications, more innovation was required. And so a lot of my research is focused on scaling up reinforcement learning. And one of the ways of doing that is by combining it with the power of supervised learning. And so at the heart of every reinforcement learning algorithm is what's known as a state value function that's conceptually trying to learn the expected future value of taking an action from that state. If you have a small set of discrete states, you can learn this with a table lookup representation. But in a large state space, you're going to need to generalize. And you can bring the power of all the recent advances in supervised learning, such as especially in neural networks, to this problem of generalizing through the state action space in a reinforcement learning problem. And so reinforcement learning has now sort of started seeing the light of day in the industrial world. It's become useful for practical applications. Back in '94, there was a famous backgammon system by Jerry Tesaro at IBM. In about a decade and a half ago, it was shown to be effective for learning helicopter control, and more recently, for some more healthcare and sustainability-related applications, such as treatment of epilepsy or invasive species management, wildfire suppression. And really, what's launched it into the public awareness is that reinforcement learning is at the heart of Google DeepMind's AlphaGo system, that beat the human Go champion very impressively a year and a half ago or so. So in my lab, like I said, we focus on how can we scale up reinforcement learning. We've done this through demonstrations, through using human feedback. So for instance, one example is here in this game of Tetris, a person can give positive and negative feedback by clicking a button. When this up here flashes red, it means that the person gave negative feedback. When it flashes green, it means they gave positive feedback. Through standard reinforcement learning methods, after thousands or hundreds of thousands of games, you can learn a very good Tetris player. With this human feedback, you can create algorithms or programs that can learn to do this in just 2 or 3 games. And even in the first game here, it's starting to make reasonable moves. And if we look just to the 3rd game of learning, it's able to start clearing hundreds or thousands of lines in the game of Tetris. And again, this is about learning the effects of actions through experience. We've also, Bruce also mentioned about the challenge of transfer of when you teach a kid to play chess, you don't typically teach them chess right away. You start with tic-tac-toe, move to checkers, move to chess, and so on, and you expect a child to be able to transfer the concepts from game to game. We've been exploring algorithms for transfer learning and reinforcement learning for quite some time as well, and we've also focused on trying to use reinforcement learning in data-poor environments, such as in robots. You can't get the kinds of you can play millions of games of Go and learn from that, but you can't play millions of games of soccer on real robots and expect your robots to still be functional. Just in the interest of time, I'll briefly talk about the Robot Soccer Grand Challenge. That's, as was mentioned in the introduction, our goal is to beat the World Cup champions by the year 2050 on a real soccer field. We're still a ways away from that. But there's been a lot of progress. If you look at RoboCup in the early years, from 1997 to 98, it was a big success at this point just to get robots working, several robots in the same room, not falling apart. Some of them did catch on fire that year, actually. But they'd fall over, they'd get up, they'd run into walls, but they at least were running. If you look ahead 10 years from there, you'd start to see in many of the same leagues much more sophisticated behavior. Individual capabilities, the robots are passing, they're moving. This was the beginning of the humanoid competition. There was just a penalty shot competition that year. But now if you look again 10 years further, the advances there are striking, and the research advances have been huge as well. So one example is there's a lot of advances in computer vision from large databases of images. On robots, the challenge is much different because you don't get static images. You get a view like this through the camera of a robot as it's trying to play soccer. Images coming 30 frames a second. It has to make quick decisions. And so different types of algorithms are needed, and we've made advances through the challenges of the demands of the robot soccer domain to the robot vision endeavor. We've also I said that our goal is to have humans play against the robots play against the best World Cup champions on a real soccer field. We're still a ways away from that, but every year we do now play against the champions of one of the RoboCup leagues. And here from a few years ago is myself and a few colleagues playing against the champion of the middle-sized robots. They always tell us it's too dangerous. The robots are gonna hurt you. They move way too fast. But then we can still, a few aging amateur soccer players are still able to pass the ball around the robots and score once in a while. I was called for offsides there, so it didn't count. But it's getting a little bit harder every year. We don't know if it's because the robots are getting better or we're getting older, but one way or another, it is getting more difficult. Just in the interest of time, I want to just close by stepping back a second. And this was all about my research and trying to emphasize what I think is the importance of grounded action learning, reinforcement learning. I do also want to just take a second to advertise a large-scale endeavor that I was a part of last year, known as the AI 100 report, which was I was invited by the AI 100 Foundation, chaired by Eric Horvitz, to conduct a study on artificial intelligence with the charge of looking forwards 15 years and also backwards 15 years to identify the possible advances in AI and their potential influences on daily life. And in particular, to specify scientific, engineering, and legal efforts needed to realize these developments and to consider the actions needed to shape the outcomes for societal good. I think this is really important. We're pushing the state of the art in artificial intelligence, but we need to keep aware of the context and for what the potential realistic benefits are, how we can get there, but also what the realistic risks are. There's a lot of risks that are sometimes, I think, overemphasized, that are completely unrealistic, and that are sometimes harped on in the press. But there are many things we do need to be concerned about. And so the AI 100 report, which I encourage you to go online and download, examines in 8 different areas shown here the progress that has happened in artificial intelligence over the past 15 years and our predicted the predictions we make for the effects and progress in artificial intelligence technologies over the next 15 years. And without going into any details, because I'm out of time, I just want to say the one take-home message that I think is most important from this report is to try to dispel the myth that artificial intelligence is one thing. I think there's a fallacy that many people, that's very tempting, that many people fall into, which is they learn that an artificial intelligence program has beaten the world Go champion, and people say, oh, I can't beat the world Go champion, but I can fold laundry and I can put away dishes, so that program must be able to do those other things as well. And that's just not true. right? Each new application requires specific research and development. And because of this, we need to resist the temptation to think of AI as one thing. It's rather a collection of technologies that need to be approached individually, need to be treated from a regulatory perspective individually. We should not be regulating AI. We should be thinking about AI in healthcare, AI technologies in transportation, AI technologies in education, and all these other areas separately and individually, and thinking about how we can maximize the potential benefits and steer clear of the potential risks. So with that, if there's any time, I'll be happy to take questions, and thanks for your attention.